Oh, look at that. You're already here. All right.
Yeah, hey, what's up?
Hey. Okay, what can I do for you? I was not expecting
Okay,
you.
so yeah, this week has been very learning intensive. I've probably been doing 2 lessons a day, every day of this week, and I just wanted to kind of ask you about my doubts, especially since I had been behind until like now, where I've fully caught up.
Okay. Yeah, I mean, 2 lessons a day is really intense. It's
Yeah.
hard for me to say much without knowing a little bit more from you. So why don't you tell me what the last few lessons were that you worked on, how you feel about them? We can talk about a few problems, and then I might be able to give you a slightly more accurate perception of kind of where we are.
Sure. So right now I just finished the last lesson on what was it, ratio and root tests,
Okay,
as well as
that's where we
absolute
learn about
convergence.
absolute
So,
convergence too. Yeah, okay.
yeah, all of that makes sense, and I feel like I've been developing a good eye for determining when things are convergent and divergent.
Okay,
And
good.
most of all, I think one of the things that I had been struggling with, especially in the homework, is actually explaining why I think things are convergent and divergent, especially when
Yeah,
it came to the direct comparison test.
okay.
Um, I know that P series with P greater than 1 are going to converge, right? And for the most case, when making the direct comparison, it's kind of easy. I think what I had trouble with is how is a constant times a P series still going to converge the same way that the P series alone would? Because I know that in integration, it is the case because you can remove the constant from the integral by just moving it outside, but not
Yep.
with sigma notation.
So yes, if you are a constant multiple of a convergent P series, you are convergent. And if you are a constant multiple of a divergent P series, you are divergent. And you can remove the terms P series from those sentences and still get a true statement. So a few things that you may want to tuck into your notes here. If we're moving, it would be easy to miss these. Is that this operator follows the same rules as this operator.
Oh, okay.
And what that means is that if you have sigma, say, an plus bn, this is the same as sigma an plus sigma bn. And if you don't mind me leaving the bounds off, right, these could all be from 1 to infinity or 0 to
Yeah.
infinity or whatever. It doesn't matter. So I'm just to save time, I'll leave those bounds off. And then also, well, so you could change this plus to a minus, right? Over addition or subtraction, and constant multiples pop out.
Okay. I had a hard time Googling that. And when I,
So if you look in the textbook, I think this is discussed in some greater detail in section probably 11.2 here. Where is this shit? Here you go. So this is under the hypothesis that sigma an and sigma bn both converge. And if they do not both converge, then there are some sort of subtleties here. Namely, like if sigma an converges but sigma bn diverges, then this sum is going to be divergent. But if both of these, say sigma an is divergent and sigma bn is divergent, then it is possible for this guy, the sigma an minus bn, to be convergent if they cancel each other out just right. So the simplest way to think of it is, yeah, if everybody is convergent, sigma an, sigma bn, and their sum and difference, then you can split them apart and pull them together as you would an integral.
sure.
But if you're looking for just the simplest way to think of it, it's definitely this. Just think of them as being like integrals.
Okay, cool.
So I had a problem in mind when you were saying that, and I'd just like to see how you would talk me through this. How would you show that this series right here converges or diverges or does whatever it does? How would we start with that?
That is, actually the one I was basing my question off of was very similar to that series.
Okay.
So I guess the only difference was that the coefficient was in the denominator, and that's why I was getting kind of confused. So just by looking at it, right? What's the I think the resolution is a little low. What's the
Oh, sorry.
exponent on the denominator?
That's a 4.
4. Okay.
Yep.
So by looking at it straight up, I can tell that if the series were to go to infinity, the bottom would get much larger, much quicker than the top part. So I can see how it could be a candidate for just looking at it as a P series. And I can see also why it would be convergent in my eyes.
Okay, so what are the ANs here that are being added up? These are 2n minus 1 or n to the 4 plus 1. What is it about these that makes you think the series sigma AN converges? I heard what you said, but could you be a little bit more quantitative? Why is your intuition that this thing converges? Remember, the bottom being bigger than the top isn't enough. Recall sigma 1 over n diverges.
Yeah.
All right, so here the bottom is certainly bigger than the top, but you still get a divergence. So what is it about this thing? What is it about these ANs that you think make that series converge?
Okay, so I mean, when we take a look at it in terms of infinity, right? First of all, we can when we're trying to reach what we're trying to compare to, when we think of things as terms of infinity, addition and subtraction really don't play much of a big role in the grand scheme of things, especially when it is, similar to that. So I would probably simplify that to 2n over n over, I'm sorry, 2n over n to the 4th.
Yeah, good, right? Subtracting 1. It's true, if this was subtracting an n cubed, that would make a big difference. But since
Yeah, it would.
a constant or adding a constant, I like what you're saying. Subtracting 1, adding 1 really doesn't make any sort of difference. So this is a lot like 2n over n to the 4 for large n.
I also just wanted to state that I'm thinking of the direct comparison over the limit comparison because in the bottom, the addition that is being made is making the sequence smaller. So yeah, if the operator was subtraction in the bottom, then I would have to default to the limit comparison.
Good. Okay. So we've got something to compare against, and your observations are perfect. That the direct comparison test is manageable here because the subtraction upstairs and the addition downstairs make AN overall smaller than this. So how would we get started if we wanted to set up the actual direct comparison test?
Okay, so here for the direct comparison test, I'm going to do a range, I guess, and call it star from that makes 0 greater, or that's another thing I wanted to ask. How do I know when it would be greater or equal to?
Let me make sure I understand the question. So first, this is a less than or equal to sign, right?
Oh, sorry, yeah, less than or equal to.
So
yeah.
One of the hypotheses for direct comparison test is that AN and BN are both positive, or at least greater than or equal to 0. So this is a necessary thing. Now, how would we know that that's true or not? Well, we look at the first few terms of the series, or we just think about whether or not this thing could be positive or negative. Certainly the bottom here, n to the 4 is always positive. You add 1 to a positive thing, that's always positive. 2n minus 1 is not always positive, right? He goes from being positive to negative at 1/2. But since I'm only letting n run from 1 to infinity, 2n minus 1 is indeed always positive. So you can kind of think of the graph y equals 2x plus 1. Oh wait, sorry, 2x minus 1 I should be drawing here, shouldn't I? Yeah.
Yeah.
Shit, I'm out of space. All right. And you know that this is at 1/2. So everywhere to the right of 1/2, 2x minus 1 is positive. So 2 minus 1 is positive for all n bigger than 1/2.
Yeah.
So that tells me that the ANs here are positive.
Oh, yeah, for sure. The thing and why I was asking is because I think in some of the homeworks or in some of the examples that you've worked through, you've also made the second operator less than or equal to opposed to less than.
Oh, so the theorem only requires this, only requires a less than or equal to. But if there is a strictly less than, like if I can say for sure that this is strictly less than this, then I could say that.
Okay.
So it's, yeah, I apologize if I haven't been 100% consistent with notation there. When I work with equality, if I have something like 1 over n squared plus 1, then I might be inclined to say that that's strictly less than 1 over n squared, because it is.
Yeah.
But it's not necessary that this be strict for the theorem to work. This would work as well.
Okay.
So if A is, let's see, if A is strictly less than B, then it's true that A is less than or equal to B as well. So if all I need is something like this, and I have something like this, then I can be happy with this as well. Does that
Yeah, I guess that makes sense. And
yes.
so just to
One is
finish
okay.
construct, yeah, to keep on just to finish that, it's going to be that is less than or equal to 1 over n to the third.
Or 2 times 1
Or
over.
2 times n to the third.
I don't think I can get rid of the 2, but
Okay.
definitely subtracting 1 upstairs makes this smaller, and adding 1 downstairs makes this smaller. So it's true. Yeah.
Okay, that's also something that I have been struggling with when creating the comparisons. I don't know if I should remove the multiplication, but now it's clear that I should.
I wouldn't, no. And if you're ever in doubt, try plugging in a few values for n to check, right?
Okay.
If I plug in n equals 2 here, then I'd have 2 times 2 minus 1, that's 3, over 2 to the 4 plus 1, that's 17. So I'd have 3 over 17. Now, if I plugged a 2 in here, I'd get 1 over 8. And 2 over 17, I don't think is smaller than 1 over 8, but it is smaller than 2 over 8, right?
Yeah.
So that would work okay.
Yeah, that was exactly the problem I was having with my homework. I had reduced it to say 1 over n to the third and realized that the statement wasn't correct because it was never, you know, and so
I could see that being frustrating. So in that case, that's a good case. That's a good, if you run into that and you can't seem to find a way to fix it, that's a good hint that you should try a limit comparison instead. If you're like, oh, you know, this is clearly the thing I want to compare against, but my equality isn't working, then I go ahead and shift to a limit comparison, unless there's something like, slapping a constant on that will make it work.
Yeah, that makes complete sense.
All right, how do we go from here?
So I would say that because the series S equals sigma, or n equals 1 to infinity of 2 times 1 over n to the third converges as a p integral because p is equal to 3, which is greater to 1.
So let's slow down just a little bit. It's a p.
Okay, sorry.
Right? No, it's all right. It's all right. You're saying the right sort of stuff. Sigma n equal 1 from infinity, 2 times 1 over n to the third. We got to pop out the 2.
Okay.
We can say that this is a p series.
Okay. Yeah.
But careful not to confuse a p integral with a p series. So it's a common half-point mistake. The thing here is a series. It looks a lot like a p integral, except it's a series, so we call it a p series.
Did I say p integral?
Yeah.
Oh, no. Okay.
This is a constant multiple, no worries, of a p series with p equal to 3, which is bigger than 1. Okay, I think this is where we were, right?
Yeah.
What now?
And with a piece, wait, because that is a constant multiple of a p-series that converges by dct n star, we can conclude that sigma n equals 1 to infinity of 2 times n minus 1 over n to the fourth plus 1 also converges.
Perfect.
Cool.
All right. Yeah, it sounds like you're comfortable with the logic and rationale behind the direct comparison stuff here. Just be careful when you're building your inequalities. And then those little vocabulary wire cross moments where we confuse or call a series an integral or vice versa, watch out for those. But yeah, it seems like your comprehension here is great.
Thank you. I appreciate it. Again, two classes a day is pretty intense.
It is. Yeah, you're asking a lot of yourself, but I'm proud of the result here. Most people, if they crammed like that, would probably not be as comfy as you seem.
Thank you. And of course, I think there's homework questions that I struggled with and remembered to take note of. There's this one that had me stuck, and I want to go back to it here for a sec.
Okay.
Okay, so it was, I do not know which homework. Oh, it's homework 8, number 7.
Okay. Oh yeah, this is cool. What have you tried so far?
Okay, so just by looking at it, to make it have more sense to me, right? I put the x to the negative nth in the denominator, right? So it's x to the n in that case. In the problem I had, the coefficients were slightly different, but I guess it doesn't matter in the grand scheme of things. And so what I had was.
Do you want to read it to me as you have it?
Sure. Mine was sigma n equals 1 to infinity of 7 to the n plus 1 over 8 to the n.
All right, and they probably wrote it like this at first with the 8 to the negative n.
Yeah.
All right, so it sounds like your first step there is good. We'll write this as sigma n from 1 to infinity, 7 to the n plus 1 over 8 to the n. And what from here?
So here, because at the moment I didn't know what my first step was, I tried to do the preliminary test of TFD, right?
You can run TFD, yeah.
But the TFD was also not that obvious.
Yeah, so the TFD here, the result that you need to figure out the limit for TFD will also tell you everything you need to know about the series. So rather than doing that, let me suggest the following algebra step.
Sure.
7 to the n plus 1 is the same as 7 times 7 to the n. Right?
Okay. Yeah.
The x times b to the y is the same as b to the x plus y. So b to the n plus 1 is the same as b to the n times b to the 1.
Whoa.
Right?
So if you then by removing that 7, it becomes a geometric series.
Very good. Yep, this is actually a geometric series.
Oh, wow.
This is 7/8 to the n. And that's sort of what you're going to need to figure out the TFD limit also, right? You're going to need to combine things together and then at some point say, oh, since this number is less than 1, the thing's going to go to 0 as n goes to infinity. But if you do it like this, you get everything all at once. So this is a geometric series.
Yeah. What?
Ratio r equal to 7/8. So the absolute value of r is the absolute value of 7/8 is 7/8.
Which is less than 1.
1. Yep.
Yeah. Therefore, it converges.
Good.
Okay. Ooh, all right.
And in this case, we could actually find the sum of the series as well. We know how to sum geometric series. Do you remember that trick? How we get the sum of the series out when a series is geometric?
Oh yeah, it's a over 1 minus r, which a is the first term, meaning 7/8 over 1 minus r, which is also 7/8.
Yeah, I definitely recommend that you think of it as the starting term over 1 minus r, because
Yeah.
you have to be a little bit careful. If this started at like n equals 5, then the first term wouldn't be 7/8, right? It would be like 7/8 to the 5th.
Yeah.
Also, watch out for the 7 outside.
Oh yeah, that's right.
First
That's
few
right.
terms of this series, the n equals 1 term is actually 49 over 8.
You're right. Okay.
This would be 49/8 divided by 1 minus 7/8.
Okay.
I always like thinking of it in terms of starting term over 1 minus r. It makes life a little
Yeah. Yeah, for sure. Yeah, because I don't know, in the definition that you gave, you said a, it's sigma whatever bounds to infinity of a times r to the n, in which a was a constant
right. So
rather than
you go back
starting
and watch
term.
that video. There's a little bit of subtlety there, and at the end I did talk about it, but it's easy to get lost in the wash with so much else going on.
Yeah.
It's true that sigma n from 0 to infinity a times r to the n will always come out to a over 1 minus r if the absolute value of r is less than 1. But not every geometric series starts at 0. Not every geometric series looks exactly like this. So this formula only holds for series that start at 0 and are written exactly like this. But the more general result, and I do talk about that in that same video, the more general result for a geometric series is this.
Is the starting term. Yeah, for sure. And so, okay, then that's one thing that you caught, because up until this point, when I've been explaining why geometric series are convergent, I use a to identify the constant rather than the starting term.
Yeah, and that works fine if your series starts at 0.
Yeah, and for the most, or at least in some of the questions, it wasn't. So I was like,
Right. Yeah, like the one we're looking at
it's
here, n starts at
different.
1. Yeah.
Yeah.
And definitely
Okay.
the test, that's one of the things I like to throw in there, is usually there's a geometric series that doesn't start at 0, which I'll ask you to sum at some point or something like that.
Yeah. Okay. Yeah, that makes a lot of sense. And in the same one, I had 15 in the same homework, number 15. And
Okay. Oh yeah. All right. So there's a few things to do here. First, you need to show, and this is like 90% of the time on this problem goes to showing that the function here is positive, continuous.
Positive, continuous, and
So
decreasing.
I don't remember one of my classes. I actually went through this problem last time. I don't remember if it was your section or the other section. Let me see here, because I got to run downstairs and grab some coffee real quick. But I think I can point you to a video where I start this problem at least. And while I'm grabbing coffee, you can look at that, and then we can talk about it together. It would have been this one, but right at the very end. Can't see shit. All right, there it is. No, this isn't it, is it? The fuck? That's not what we asked for. Maybe it was this one. Special limits. Ah, shit. Maybe not. Maybe it was a little earlier. I think it was this class. I think it was just a few minutes before this. Yeah. Okay. Here we go. Where does it actually start? It actually starts like here. This thing takes forever. Yeah. Okay. So let's pause, share, grab the link starting at that time, copy. I'm going to send this to you in the chat, and you can watch the first few minutes of this while I go refresh my coffee, and then I will be right back. So here's
Sure.
the
59, okay.
Yep, and it should start right at that time, but if it doesn't, go ahead and advance to 59 minutes, 49 seconds,
Perfect.
and I'll be back in just a couple.
Sure, thank you.
Okay. Sorry about that. So,
You're good, you're good. So, yeah, essentially what made this problem difficult was proving that it was decreasing. And that's
For
why
sure.
I was like, I don't know where to begin. And even like differentiating this, it's not like a
It's still not
straightforward, very easy derivative to just pop
No.
out. So I would understand why like the largest part of solving this problem is explaining why it's decreasing.
Yep, and that's always the case with these integral test problems. So the bulk of the time goes into proving that the function is decreasing, unless you get really lucky and it's like the reciprocal of some obviously increasing thing.
Yeah,
But
this definitely isn't.
definitely, if f primed is less than 0, then f is decreasing. And there, f of x was something like x to the 6 e to the negative x to the 7 or something horrific like that. So this derivative requires the product rule and the chain rule.
Yeah.
Something like this. And so here this would be a 6x to the 5. That one's not hard. And then this is x to the 6. And this guy is a chain rule thing. So when you differentiate e to some shit, you always get e to that shit back.
Yeah, of course.
And by the chain rule, I need to multiply by the derivative of the shit inside, which is negative x to the 7. So that's negative 7x to the 6.
Yeah.
So this is what we get just from that. And unfortunately, showing that this thing is negative is not simple because it's not always negative. So first I would write it 6x to the 5, e to the negative x to the 7, minus 7x to the 12, negative x to the 7.
Yeah.
They're all multiplied. So this and this. And then you can factor out as much as you can. I guess like x to the 5, e to the negative x to the 7, and that will leave us with 6 minus 7x to the 7. And if you're lucky, when you do this, you'll get something relatively simple here.
Yeah.
This stuff is positive, right? Definitely x to the 5. If x is positive, x to the 5 is positive, and e to the x, or e to some stuff, is always positive. So the sign of the derivative follows from the sign of this piece. And the sloppiest, fastest way to get this done is to talk about end behavior. So I don't know how far you made it in that video. I know I was gone for a second. The end behavior of this polynomial is definitely negative because he's an odd degree with a negative lead coefficient. So I don't know what the hell he does in here, but eventually that sumbitch is heading to the floor.
Yeah, it's gonna be heading down.
So there will be some value after which this thing is negative. So f primed of x is less than 0 for all x greater than, say, this, whatever that capital N is, which means f is decreasing. And that's really all that we care about, is that eventually this function is decreasing. The way the theorem says it is that we need f of x to be decreasing everywhere on the interval 1 to infinity, but that's not actually true. Because I can pull out the first 10 terms of the series and then just start the series from that decreasing point on. And whatever those first 10 terms were, they're not going to make the series diverge. So this, in practice on the test and whatnot, I won't give you problems where you know, I'm not trying to test your inequality solving skills here, right?
Yeah.
So I don't want to give you some nasty polynomial times exponential inequality to solve. Whatever you have to work with when it comes to this stuff on the test will be much simpler, or at least a little.
Okay. Yeah, that's completely fair, because the integral of it, and why I left it blank, the integral of that is a fairly simple integral.
It is.
It is
a
a
U sub thing.
U sub. And the reason I didn't want to do it was because I didn't know how to prove that was decreasing, or at least I was just like floored by it, because in the beginning it wasn't obviously something that goes, it's not the reciprocal of an increasing function, or at least it's not obviously. And another thing I wanted to add was that when I started doing it, I didn't use the product rule. I used the division one, which is u prime times v minus u times v prime over u squared, I think.
Yeah,
And
attack
or
it
v
like
squared, I'm
this.
sorry.
Yep.
Which also made it not intuitive. It's actually more straightforward to do with the product rule.
I agree. Yeah. The quotient rule here is not as nice.
No. And that's why when I was looking at it, I was like, man, I have no clue.
Yeah.
But I get.
Yeah, go ahead.
No, I mean, really, those were the things that I had been caught up on. I'm looking at the homework, and everything seems to be relatively easy. Alternating series is very straightforward.
It is.
The last two are very straightforward. The tests aren't like too crazy.
I agree. Yeah.
I think just the beginning, like understanding how to do or how to construct their comparison, and then the comparison was something that I struggled with. And the integral test proving all of the things is also not fun. But other than that, I guess I feel very confident in my ability to determine convergence.
Okay, good.
Now, here's the last question, because I know we're going to be talking about integrals, since I forgot what section it was.
7.8.
7.8. So I don't remember very well what we were talking about there. Or were we talking about convergence, P integrals, stuff like that? Okay.
Yeah, so there's two types of improper integrals.
Yeah, type 1 and type 2.
Yeah, the ones with infinite length or width, however you want to think about it, these are called type 1. And these are integrals either from like negative infinity up to a of f of x dx, or integrals from a to infinity f of x dx. They're things that, you know, look like maybe this. I'm trying to find the area going all the way out. So this would be like a negative infinity up to a f of x dx integral, or maybe you've got something like this. I want to find the integral from a all the way out to infinity. So there's something that looks like that. And in both cases, we end up writing them as limits. We write this integral from negative infinity to a f of x dx as the limit r goes to negative infinity. Ah, shit, my handwriting. Negative infinity integral r to a f of x dx. and the integral from a to plus infinity, we write that as the limit r goes to plus infinity, integral a to r, f of x dx. So those are what type 1 integrals look like and how we set them up. And if these limits exist and are finite, if the limits defining the integrals right, these limits exist and are finite, then we say, then we call the integrals convergent. Otherwise, we call them divergent.
Okay. All right, so I guess I do remember a lot of that then.
Yeah, type 1 integrals aren't too bad, especially if you remember series. Think of type 1 integrals as being a lot like infinite series, just kind of continuous instead of chunky. But type 2 integrals are weirder.
Yeah, because they have, what's it called? Asymptotes.
Yeah, so type 1 come from infinite kind of length or width. Infinite height these are type 2. And they don't look weird. This is like if you write down the algebra, they don't look strange. You have to kind of think carefully about the picture.
Yeah.
Yeah, and like you said, yeah, asymptotes, right? So yeah, let me call this this number right here b. So if I want to do the integral from a to b, and f of x has a vertical asymptote at b, that is definitely an improper integral because that region is infinitely tall. Or if I wanted to do the integral from like b to c here, that would also be an improper integral. So the integral here from a to b, f of x dx, I would have to treat this as the limit as r approaches b from the left of the integral from a to r. And if I wanted to do the integral from b to c, that's to find the area on the right of the asymptote, that I would treat as the limit as r approaches b from the right of the integral r to c f of x dx. So these are the kind of two setups here. So f of x has an infinite discontinuity. So I've drawn it here. F of x has an infinite discontinuity at x equals b. And if the infinite discontinuity is at one of the endpoints for your integral, one of the bounds, then we know how to set it up. And if it's in between the bounds, like if I wanted to do the integral from a to c here,
Yeah.
I would have to first split it up as the integral from a to b
Plus the integral from b, c to b, c to c.
Yeah, perfect. And then each one of these, I would have to use a limit like this to define. So that's your type 2 integrals. Type 2 are a little
That's actually,
Go ahead.
No, that it was actually very helpful. I completely forgot that I had to, at least when constructing it from, A to C, I forgot that I had to find the limit from the left and the right when constructing it and putting it back together. So that's a good note.
Good. Okay.
Um, Also, this might not be in the test, but it's still a general curiosity that I had. What happens when a series is, I'll call it a type 2 series, has discontinuity in its bounds?
Well, so sequences don't have a notion of continuity the same way functions do. This type 2 behavior is only really possible because I can let my x's get closer and closer and closer to b.
Mm-hmm.
Can't do that with a series because n always has to be a whole number. But I know what you're asking. You're asking like, what would the series sigma n from 1 to infinity, or maybe just from 1 to 5 of like 1 over n minus 2 look like, right?
Yeah.
Because here this guy blows up at 2 and 2 is in between these. This, we would just say this isn't defined.
Oh, okay. So the answer does not exist. So
Yeah, because 1 over 2 minus 2 does not exist. I can't sneak up on things. I can't take limits at finite values for sequences the way I can for functions of a continuous variable. So there's no way to like sneak up from the left, sneak up from the right,
yeah.
and try to get a limit there.
Yeah, no, you're right. You're right. Okay.
I'm actually not aware of any, I've never actually seen anybody try to handle one of these things formally, but I imagine the first step would be to relate this to an integral and then do the integral.
But then you couldn't do the integral test because it's discontinuous.
Right, well, certainly not the integral test. This would be a totally different animal, but I think the closest thing you could do to making sense of this would be to relate it to an integral and then compute that integral. However, certainly the integral test does not apply. No, it would have to be its own thing.
Okay. Well, this has been very helpful.
I'm glad.
I
I'm glad.
really appreciate you taking an hour before the office hour to kind of help me
I'm
answer the
happy to
questions
do it.
that I had.
Now, I do think there are a couple other folks who wanted to chat with me about something somewhat in private before we begin the formal thing. So I'm going to go ahead and assign each of you three to separate breakout rooms. And then I'm going to come in and visit you guys to talk about whatever thing we wanted to talk about in private. So give me just one moment.
I don't have anything to ask in private. If anybody just
Okay.
has regular questions, you can just put me with that person.
All right.
Yeah.
Talk to it.
Now,
Actually, you answered all my questions, I think.
okay.
Yeah. So really appreciate it. See you
Yeah.
in testing.
Happy to do it. Eddie, I would encourage you to stick around because for the next hour, I'll be doing just random questions from other people. But if you got to bounce, you got to bounce. But yeah, either way, happy to have worked with you and talked.
Sure. It's I haven't eaten yet, so.
Oh, okay. I totally understand. No worries.
Yeah. Take care. Thank you.
Now, I think everybody should have. So if you gotta go, you got to go. That's fine. Otherwise, go ahead and join the breakout room and I will come in and talk to you one-on-one. Daniel, did I get you here? Everything work okay? Oh shit, what happened? One unassigned participant. What? Okay, Daniel, did you need to talk about anything with me before we get into the big review? I don't remember.
No.
No, you good? Okay, cool. Sorry, I had a few people message me and asked just to have a quick chat about grades or something before we got started here. But if you are comfy, then I will go ahead and move you back into one of the other rooms and see if there's anybody else here who needed to talk about something. All right, Demidar, you said you're doing good, right? Is there anything you needed to talk about grade-wise or other stuff before we get started with the main review?
No, I think I just have regular questions, but now it's the time for the general office hour for everyone to be there and ask questions. So I will just ask questions there.
Okay, sweet. All right, I got to check in on one other person and then we'll be ready to get started.
Great.
Let's drop him in here. I will join as well. Jack, you doing good? Did you have anything you needed to talk to me about one-on-one before we get started with the main review stuff?
Not one-on-one. I mean, I have, just normal questions, but
Okay, cool. All right, then I think that takes care of everything. I'm gonna go ahead and close all the breakout rooms and we'll get started.
right.
Okay, we should have everybody back here now. All the rooms are closed, good. So we can do whatever you guys would like to do. Whatever sort of problems you guys want to work, whatever sort of examples you want to see, I'm happy to do them. If you want to go over solutions or talk about concepts, draw pictures, or whatever. So just go ahead and let me know. Remember, you can hold spacebar to unmute yourself, or you can type in the chat to talk. Tell me what you'd like to see. What can we do?
Can you do 25 from homework 8?
Sure. All right, 25 from homework 8, and we got number 14 from the study guide. I'm gonna do the homework 8 problem first. Let me flip on my screen share. All right, is this the one we're thinking?
Yes.
We want to find all the values p such that the sum from 1 to infinity, I'll write this down and then I'll switch back. N cubed times 1 plus n to the 4 all to the p converges. Okay. And it looks like the n cubed term that I have here, you might have something else. You might have n minus 1 to the 7 or something like that. But it should be looking fairly similar to this. I'll tell you what I see when I see this. N cubed times 1 plus n to the 4 all to the p. This is literally the same as sum from 1 to infinity n cubed over n to the 4 plus 1 to the p, like this. Sorry, to the negative p. All right, so I can bring this term downstairs by negating the power. And then I would say, so here an is n cubed over n to the 4 plus 1 all to the negative pth power. And for very large values of n to the 4 and n to the 4 plus 1 are basically the same. They're only off by a little difference. So this is really the same as like this for big values of n. And that's the same as this, and for large values of n, which is the same as what is that? This. This is all for large values of n. So I suspect that the series will converge provided negative 4p minus 3 is strictly greater than 1. Right, because this would be a p-series. Because sigma an is very similar to sigma 1 over n to the negative 4p minus 3, which is a p-series. So I need the power down here to be bigger than 1 for the series sigma this stuff, right? Sum from wherever, 1 to infinity. For the stuff, for the series to converge, I need that power there to be larger than 1. So when is negative 4p minus 3 greater than 1? Well, I can add 3 to both sides. 1 plus 3 is 4. So I need p here to be less than, flipping because I'm dividing by a negative. 4 divided by negative 4 is negative 1. Now, if we want to make this rigorous, we would have to do a limit comparison. To make this rigorous, I would limit compare this series against this series, right? My series, I'm claiming, is very, very similar to this p series. The way to make this rigorous is via a limit comparison, but the problem here is just asking you to determine the values of p for which the series converges. So this sort of argument would be sufficient. That is, it'll get you the right answer. Do we want to see the detail there, the limit comparison? Are we feeling okay with this? What are you guys thinking?
I think on the homework it asks to find the limit if it converges.
Well, so remember we're dealing with a series here. So if the series converges, you would have to find not the limit, but the sum, right? Which is, taking the limit as n goes to infinity here isn't exciting, but trying to find the value of this sum, that would be exciting. However, that's incredibly hard. And definitely for this problem, we're not asked to do that. We just have to tell them that p has to be whatever it is, less than negative 1. There are other problems that ask you to find the value of the sum, but those won't be problems like this. Those will be problems where the series in question is either telescoping or geometric, because to actually find the sum here is incredibly hard. 26, which is
I have
one
a
we did
question.
in class. This one does ask you to find the sum of some series by relating it to the sum of another known series. Yeah, question?
Yeah, can you, like, when you get to 1 over n to the power of negative 4 p minus 3, you already know that p is negative 1. Could you just leave it there, or do you have to, like, explain the whole thing?
Well,
Like, could you?
arriving at this is how I knew to say this, right? I didn't know that p was negative 1 from this. I knew that that power has to be bigger than positive 1. And then we had to solve to deduce that p is less than negative 1. There isn't really any other work between here besides explanation, right? And explaining is important. So remember that what we're doing here is we're essentially writing proofs. The communication is at least as important as the calculation. If you gave me this work and then you jumped straight to saying p is less than negative 1 without saying anything about p series or why p has to be less than negative 1, I couldn't give you full credit. I could give you majority credit, sure, maybe 4 out of 5 points, but you've got to tell me why this leads to this. You got to give me some explanation. And the basic gist is that the thing we're adding up is very similar to this. So our series is very similar to the series of those. And this thing converges if and only if that power is bigger than 1. So you got to have some explanation. There needs to be logic there which I can follow and verify is correct. Does that make sense?
Yeah, that's fair enough. Thank you.
Yeah, it doesn't have to necessarily be as detailed as this, but I need some sort of explanation. Other questions here? Or comment?
Yeah, so why would we want to do the limit comparison test if we already know that it converges from the P series?
Well, so what does the limit comparison test do? It tells you whether or not two series do the same thing. So right here, I'm saying AN is very similar to this, but that's not at all rigorous. What does it mean to say is similar? What do I mean by approximately equal to? How do you know that this being approximately equal to this in any way guarantees these series will do the same thing? It doesn't. You know, it's just a play of words. It's just me connecting things together without anything to back them up. The limit comparison test is what I would use to back this claim, that our series does the same thing as this series. So the limit comparison test wouldn't help me find the values P. It would help me connect the series they gave me to this series to guarantee that my series converges exactly when this series converges. So LCT here would be to say, would be what I need to say that my series really does do the same thing as this series. And then this series I know is a P series and it'll converge exactly when that power is bigger than 1. But in order to then go from this series back to the series they gave me to say that my series converges for the same values of P that this series converges for, that's where limit comparison test would be necessary. Is that making sense?
Yeah, I got it.
Okay. Yeah, remember how LCT works. It says if lim n to infinity an over bn equals c, where c is positive and finite, then the two series sigma an and sigma bn do the same thing. So it's the limit comparison test that I would use to connect the P series that I can use to figure out the value of P I need with the series they gave me, because the series they gave me wasn't actually a P series. It was just kind of similar to a P series. And the limit comparison test would let me make that similarity statement rigorous. Other sort of questions or comments here?
Just a quick question. Why did you change the which way the greater than sign was facing at the end?
Because I divided by a negative. So anytime you multiply or divide through an inequality by a negative number, you have to flip the sense of the inequality. So here
Okay.
I did both sides by -4 to go from this to this. So I had to flip over the inequality.
Okay.
How likely is this question in the test though?
This exact question, 0% probability. A question similar to this, depends on what you mean by similar. There will be at least one question on the test that says, for what values of the following parameter does the series converge? Something like that will show up.
Okay, cool. Thank you.
Mm-hmm. All right, what else, guys?
Number 21 on the latest homework. Not the study guide, but the homework.
All right. Oh, and I'm forgetting, somebody asked for a study guide question in between, didn't they? Where was that in chat, right? Where'd my chat window go? Oh, sometimes Zoom, I hate you. There it is. Okay, so before we go to that one, I'm going to look at number 14 from the study guide, and then we'll go to that more recent homework. Because I think Connor asked this earlier. And study guide problems being study guide problems. I don't want to solve the exact one, but I will solve something similar, which will hopefully give you the gist of what to do for the study guide problem. The series in 14 here, I like these a lot because they're evocative of something that hopefully you guys remember from Calc 1. Does anybody remember having to figure out this limit? In Calc 1? It's usually done around the 3rd week when you're cooking up the derivative of sine and cosine for the first time, maybe 4th week. Or does anybody remember what this limit is?
Is it?
It's like
isn't
a
it one?
fraction or
What?
something, right?
It definitely looks like a fraction now, but the value of the limit is an integer. What was the other comment? I couldn't hear.
1.
Yeah, this is 1. And you cook this up before you had L'Hopital's rule. So you can use L'Hopital's rule for this. It looks like 0 over 0, and L'Hopital's rule will give you that this limit is 1 right away. But in Calc 1, the very first time you do this, it's quite painful. Usually it's done by comparing some areas. I'm not going to go through the whole thing here. It's a pain in the ass. But you're able to say that the area of the big triangle is larger than the area of the small triangle, and all of that is contained within the area of the sector, and then you use the squeeze theorem and you get 1. Okay, but it doesn't matter. The fact that this is 1 means that the sine of something is very, very close to the thing inside if the thing inside is close to 0. So for example, the sine of 0.01 is close to 0.01 itself, or the sine of 1 over 150 is close to 1 over 150 itself, or the sine of 1 over n to the p is very, very close to 1 over n to the p itself, as long as n is big. You may have heard this if you've taken physics, referred to as the small angle approximation. These are all special cases of just like sine theta is approximately theta for theta close to 0. Physicists call it the small angle approximation for sine. Works for tangent also, because the cosine of 0 is 1. So if I'm handed a series that looks like this, and I did put this on an exam one year, students wanted to kill me, I could ask you, for what values of p does this series converge? Well, according to what we've said above, this should be pretty similar to this. And you could make that rigorous with a limit comparison. So I'm showing you all of this, which is way more than we need to solve the problem, just to try to give you a little bit of an intuition for how problems like this go. So let me jump in with a problem like ours. How about this? Tangent of 1 over the square root of n summed from 2 to infinity. I know that tangent of theta is sine theta over cos theta. If theta is close to 0, then the bottom is 1, either close to 1, and the top is just sine theta, which is approximately theta for theta close to 0. So tangent of 1 over the square root of n is close to 1 over the square root of n for large n. But there's no obvious inequality. Tangent of 1 over root n is definitely not smaller than 1 over root n, it's just close to it. So I need to run a limit comparison test. I pick my bn's to be 1 over the square root of n, or whatever is inside the tangent or sine function here. Then c is the limit as n goes to infinity of the an over the bn, which is the limit as n goes to infinity of the tangent 1 over root n divided by 1 over root n itself. As n goes to infinity, the top here is going to the tangent of 0, and the bottom is going to 0, which is just 0 over 0. So I can use L'Hopital's rule. The derivative of the tangent of 1 over n, or 1 over root n, is secant squared of 1 over root n times the derivative of 1 over root n, right, using the chain rule. And then downstairs, I just have the derivative of 1 over root n. So without even computing that derivative, I can cancel these things. And the derivative we could figure out, it's a power rule derivative, but we know it's going to cancel because it shows up here as a part of the chain rule and down here on its own. So I just get the limit as n goes to infinity of secant squared of 1 over the square root of n, which is secant squared of 0, which is 1. Now, since c equals 1 is positive and finite, the two series sigma n from 1 to infinity tangent of 1 over square root n and sigma n from 1 to infinity 1 over square root n, these do the same thing. They converge or diverge together. That's what the limit comparison test tells us. It tells us that these two series do the same thing. What's more though, I know what the second series does. So we'd say, moreover, sigma n from 1 to infinity 1 over square root n, that's sigma n from 1 to infinity 1 over n to the 1/2 is a p-series with p equal to 1/2, which is not bigger than 1. So p diverges. Thus, by the limit comparison test, our series sigma n from 1 to infinity tangent 1 over the square root of n, this diverges also. All right, so I'm going to zoom out a little bit and try to get you most of the thing on the board at once, or on the cam at once. Yeah, pull this out. There we go. And we can take a second, ask questions, think about it together. All right, so what are we thinking? The actual solution begins here. All right. All the stuff before that is just discussion, trying to help you guys see why I chose the BN the way I did. Thoughts, feelings, comments, complaints?
No, I mean, this is, I understand what happened here, so that's cool.
Okay, yeah. Anybody have anything that they're concerned about or that they'd like to talk about a little more? Anything or like where did this come from or why did we do that or why write this that way?
Ooh, I have a question. In general, when it's like the series of 1 over n, we automatically say it's divergent
Yeah,
because it's like a common harmonic thing.
yep. And you can use that as a fact on its own. You can just tell me that sigma 1 over n diverges as the harmonic series. Or you could say that it's a p series with p equal to 1, which is not strictly bigger than 1. Either of those would be fine. So there are proofs of divergence of the harmonic series that don't depend on it being a p series. And both of those are totally valid. All right.
How does the secant 0 become 1?
Oh, remember secant of theta is 1 over the cosine of theta. So secant squared of 0, that's the square of 1 over the cosine of 0. The cosine of 0 is 1. So that's the square of 1 over 1, which is 1.
Okay, thank you.
Of course. Other questions on this guy? Or any other parts of this guy? Okay. So there were a couple other questions there. There was one from the latest homework. I think what was that next one that was asked?
Question 21.
From homework 9?
Yeah.
All right. Yeah, this is a good one too. I get that right. Yeah. All right. They're kind enough here to tell us to use the root test. If they hadn't told us to use the root test, though, we could have deduced that the root test would be useful because I've got a bunch of stuff being raised to the nth power. Right? In fact, it's being raised to the n squared power. So when you take the nth root, it'll become nicer. My first step would be to pop out the 4. So we don't have to deal with it as we work through the root test. Constant multiples pop out. So then, remember what the root test says. It says you calculate L as the limit n to infinity nth root of the absolute value of an. And then if this number L is less than 1, the series converges absolutely. If L is bigger than 1, then the series diverges. And if L is equal to 1, then I don't learn anything. Here, that's the limit as n goes to infinity of the nth root absolute value 1 plus 1 over n to the n squared. Thankfully, everything inside here, 1 plus 1 over n, all to the n squared, that's definitely positive, right? 1 is positive. 1 plus 1 over n is then definitely positive because n here is going from 3 to infinity. Take a positive number, raise it to a power, it's going to stay positive. So I can lose the absolute values. That's not always true. So you got to be really careful about making sure that the inside is positive, but here it is.
What happened to the 4?
I popped the 4 out. So I'm applying the root test to this series. All right, I popped the 4 out. If the series converges, 4 times that series converges. Remember, the sigma operator follows the same rules as the integral operator. So you can split up over addition and subtraction, you can pop out constants. It's what's called a linear operator. It might be worthwhile. One of the things I really recommend people do as we get close to this test is come back to section 11.2. We get so deep in the woods with all these different tests that it's easy to kind of forget the basics. So I would definitely recommend coming back to section 11.2 and reading and even maybe writing down all of the theorems here. And one of them is this, which says like constant multiples pop out. You can split up over addition and you can split up over subtraction. The thing that you need to watch out for here is that all the series involved need to be convergent in order to split up, but always constant multiples pop out. This first one has the least kind of subtlety to it. So I popped the 4 out and now I'm working just with the series without the 4. My next move here is going to be to rewrite the nth root as a power. So remember, a square root is the 1/2 power. So the nth root is the 1 over nth power. And then I have a rule for exponents, which says if you take something, raise it to a power, and then you raise all that shit to some other power, that's the same as taking this thing and raising it to the product of those powers. So this is 1 plus 1 over n, all raised to the power of n squared times 1 over n. And n squared times 1 over n, that's just n. So this is the limit as n goes to infinity of 1 plus 1 over n to the n. So sort of things I'm using here. Nth root is the same as the 1 over nth power. And then a to the b, all to the c, is the same as a to the b times c.
Professor, In like when we're writing out our problems, would you like us to write those?
No,
the
no.
examples?
Yeah, no, you don't need to do that. I'm just putting that in for anybody who's having a hard time seeing. No, you certainly don't need to. I trust if you do your algebra right, I don't need explanations. So what is this limit?
E to the n.
Not e to the n.
Just E.
Yeah, just e. So remember the limit as n goes to infinity of 1 plus a over n all raised to the b times n. This comes out to e to the a times b. So this fellow right here has a and b both has 1. Which is just e.
Is there a reason why it's not 4e? Because you pull out the constant, don't you eventually have to multiply it at the end?
This isn't the value of the series. This is the limit from the ratio test. Right? I'm not saying that the series is equal to e. I'm saying that the number L you calculate from the ratio test is e. Even if I included the 4 inside the ANs, it would have gone away. I can be clear about that. If I decided to not pop out the 4, then L would look like limit n to infinity nth root of 4 times 1 plus 1 over n to the n squared, which would be a limit n to infinity 4 to the 1 over n times 1 plus 1 over n to the n, which would be 4 to the 0 times e, or 1 times e. The limit L here from the ratio test was going to come out to e whether I included the 4 or not. But popping out the 4 just saved me having to do any calculations with it. And I'm not claiming that this is the value of the series. All right, this is not equal to S. This is L. L is the limit from the ratio test, has no direct algebraic relationship to the series. So the 4 doesn't come back in here. This is just the number that you calculate, the statistic, if you like, on the series that we can use to tell whether or not the series converges. You could have included the 4 in your ANs, in your calculation there, but then you'd be taking the nth root of 4, which tends to 1 as n goes to infinity. So regardless of whether you included the 4 in the ANs or not, the limit L here would be e. And the idea is that multiplying by a constant has no effect on the convergence of the series.
Thank you. That was what I was confused about. I didn't know why it was just e.
Okay, yeah, no problem. So what do we say about the series? First, is the series equal to e?
No.
Is the series equal to 4e?
No.
Okay, good. What do we know about the series?
That it diverges by the root test because E is greater than 1.
Excellent. Yeah, this is like 2.718, which is definitely bigger than 1. So the series S diverges by the root test. I know nobody made the claim, but I want to take a second to say something. Something that I see a lot when I grade these tests is like sigma whatever, you know, n equals 1 to infinity of 4, 1 plus 1 over, and I'll just use this as an example, is equal to limit n to infinity 4, 1 plus 1 over n to the n squared. This is definitely not true, right? And in general, sigma an is not equal to the limit of the ans, nor is it equal to L from the root or ratio tests. So be careful with your equal signs. All right. Sometimes we do want to calculate this limit, but it isn't equal to the series. So I would be very careful about where you put equal signs. Definitely, it is not true that the series sigma an is equal to any of the limits from the root or ratio or limit comparison tests. So those limits that we calculate when we're working with these series are just statistics that are useful to help us infer things about the series, but they're not equal. The right thing to conclude here is exactly what you just said, that because the limit L from the ratio test came out larger than 1, the series S diverges. Or here, root test, sorry, not ratio test.
How many points would you take off if we did that series equals to the limit?
Depends on what you conclude. So if you were to write the series is equal to the limit, go through, calculate the limit correctly without making any errors, and then tell me that the series is equal to E, that the series therefore converges and is equal to E, then I can't really give much credit for the problem at all. Because the series certainly isn't equal to E. In this case, the series is like plus infinity, it's divergent. But it would depend on how you tried to connect the things logically. It would depend a lot on the words that you wrote. If you were working with the root test and you happen to just put an equal sign between this series and this limit, you calculate the limit to be E, you say E is bigger than 1, so the series diverges by the root test, but you just happen to have an equal sign where it didn't belong, then that would be like a 1-point mistake. But if you made the higher level concept confusion of saying that the series is equal to the limit, and then tell me that because the limit is finite, the series converges or something like that, then that would be a much larger penalty. That would be something like a 2 or 3 point penalty.
Okay.
So it's important in our heads that we understand the concepts, right? And those mistakes, depending on what's underpinning them, can be little mistakes or big mistakes. And I'll try to put that together based on the other work on the page. Yeah, if it's just a stray symbol, that's a small mistake, usually 1/2 or 1-point mistakes. If it's a symbol that isn't stray, that you put there because of a deeper concept confusion, and I don't see anywhere you try to clarify or show me that you understand the concept more deeply, that's like a 2 or 3-point error.
Could you do a question like number 13 on the study guide, one that involves like factorials?
Yeah. Now 13 and 14, I actually don't see, oh wait, this isn't the study guide, is it? That's homework. All right. So depending on, I sent this to people in both sections. So depending on the section you're in, you may have or may not have heard this. The number L that's calculated by both the root and the ratio tests is kind of the closest thing to a common ratio that the series has. Like if you apply the root or the ratio test to a geometric series, you will get out the common ratio for that geometric series. So when I look at something like, oh, where did it go? No, it's still, when I look at something like 13 in the study guide, here I see a 2 to the n, an n cubed, and then downstairs an n factorial. So if I ignore the n cubed and n factorial, 2 to the n on its own, sigma 2 to the n, that would be a geometric series. So I'm expecting the limit here to involve a 2. The n cubed, if I divide consecutive terms that look like that, n plus 1 cubed over n cubed, that will go to 1. And then the factorial downstairs is more interesting. So I think if there's a challenge here, it's understanding the factorials. Let me construct something kind of similar here. Let's do 7 sigma n from 1 to infinity, 7 to the n times n squared minus 1 over n plus 1 factorial. Let's fuck things up a little bit, but same basic idea.
And just like an unrelated question, are you going to be posting the recording onto YouTube?
This one, I can, yeah.
Nice, cool.
So here, an is 7 to the n squared minus 1 over n plus 1 factorial. What is an plus 1 like this?
Would we put we substitute anywhere we see n for n plus 1?
Good. So 7 to the n becomes 7 to the n plus 1. N squared minus 1 becomes n plus 1 squared minus 1. And n plus 1 factorial becomes n plus 1 plus 1 factorial. And I really recommend the use of parentheses like I am doing here. Like, be very careful. Bring this up just a smidge till I can see that. Yeah, and then we'll zoom in a smidge more. Okay. Now I can clean this up. Of course, this is 7 to the n plus 1 times n squared plus 2n plus 2 over n plus 2 factorial. So the limit from the ratio test, L is the limit as n goes to infinity, absolute value of an plus 1 over an, which is the limit as n goes to infinity, absolute value of 7 to the n plus 1 times n squared plus 2n plus 2 all over n plus 2 factorial, and then I'll divide by the reciprocal. I'll divide by n by multiplying by its reciprocal. So that's n plus 1 factorial over 7 to the n times n squared minus 1. All right, so that's our ratio test limit. And it's looking a little messy. But everything here is multiplied. So I can kind of shuffle the order around, and I'll put the 7s together, the quadratic stuff together, and the factorial stuff together. And get limit n to infinity, absolute value of 7 to the n plus 1 over 7 to the n times n squared plus 2n plus 2 over n squared minus 1 times n plus 1 factorial over n plus 2 factorial. And one of the nice tricks here is to keep chunks as chunks, right? Like if you've got pieces that kind of look like they belong together, like the n squared plus 2n plus 2 and the n squared minus 1, rather than like distributing the 7 to the n over that, they're totally different looking animals. Give yourself one fraction with the 7s, give yourself one fraction with the quadratic stuff, give yourself one fraction with the factorial stuff. Put like things together. Because the ratios of those similar pieces will be easier to compute individually than they would if you distributed everything and put it all in one single piece. So 7 to the n plus 1 over 7 to the n, what is that?
Would it just be 7?
Yeah, forget the limit, just algebraically, that's 7. If I renormalize this piece, I'll get 1 plus 2 over n plus 2 over n squared divided by 1 minus 1 over n squared. And if I write out the factorials here, n plus 1 factorial is n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. It's the thing inside the factorial times the thing right below that times the thing right below that times all the way down to 1. And then the same sort of thing works for n plus 2 factorial. N plus 2 factorial is n plus 2, the thing inside the factorial times whatever the number is right beneath n plus 2. Well, the number below n plus 2, one less than that, is n plus 1. The number right below n plus 1, that's n. The number right below n is n minus 1. And this goes all the way down to 3 times 2 times 1. All right. So the n plus 1s cancel. The n's cancel. The n minus 1s cancel. Does the n minus 2 cancel? Is there minus 2 downstairs?
Would they not cancel since there's n minus 2 over an n plus 2?
Well, this definitely doesn't cancel with this. My question is, there's a bunch of shit hiding in the dot dot dots here. Is there an n minus 2 hiding in the dot dot dots here to cancel with this guy?
Yes.
Yes. Yes, there is. All this stuff cancels. You have to think about what factorials look like and how they operate. Again, depending on the section you're in, you may or may not have heard this explicitly. If m is greater than n, then m factorial contains a copy of n factorial. This is true, right? Think like 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. So take any smaller number than 7, 1, 2, 3, 4, 5, 6. There is a copy of that factorial hiding in 7 factorial. Like right here is 5 factorial. So since, what did we have? N plus 2. Since n plus 2 is greater than, what was the other one? N plus 1. There is a copy of n plus 1 factorial inside n plus 2 factorial. In other words, when I look at my n plus 2 factorial in this ratio test, I know that it has all the terms to cancel with n plus 1 factorial. N plus 1 factorial, n plus 2 factorial. Hiding inside of n plus 2 factorial is an entire copy of n plus 1 factorial. So I know this whole thing should cancel. And when we write it out, we're just trying to see what from the n plus 2 survives. And it's just the n plus 2. If I was writing more terms of the n plus 2 factorial, the next term I would have written would have been n minus 2, and you would have seen the cancellation explicitly. And when I do these problems in class, usually I write those terms so that you can see the cancellation explicitly. But when you're solving them, you need to know whether or not it's there. So I wanted to stop for a minute and ask. Is everybody clear on why the n minus 2 here does cancel? There's an n minus 2 hiding in the dot dot dots. Are there any questions about that? Okay, any other questions so far?
I'm just a little confused when you were just at the very beginning when you're doing an plus 1, you have you're simplifying it at the top, but n plus 1 squared minus 1, shouldn't that just be n squared plus 2n? Because the n
Oh,
plus
you're
1
right.
squared-
Yeah. That's a minus 1, not a plus 1. Sorry, I was treating it like that was a plus 1.
Okay,
You're right. This should just be that.
I didn't know what I was.
No, you're good. I don't know how I made that mistake myself. Yeah, so this should just be this. Yeah, much better. Thank you. Perfect. Yeah, absolutely correct. Okay, any other questions or comments so far? That is a good catch. if we're feeling good, the 2 over n goes to 0, the 1 over n squared goes to 0. So we're going to get out of this 7 times this whole piece is going to go to 1 times here I'll have left the limit as n goes to infinity of 1 over n plus 2. Everything else is canceled. So I get 7 times the limit as n goes to infinity of 1 over n plus 2, which is 7 times 0, which is 0, which is less than 1. So the series here converges absolutely by the ratio test. All right. I may have time for one more. Is there anything lingering that we absolutely want to see? Any sort of last minute stuff?
Could you do number 15 for the study guide?
I can look at something similar. Is that this guy?
Yes.
This is very similar to one we did earlier. So I can kind of show you how to set this up. You remember the series we looked at the start of the review here? We played with this guy. I think he was summed from like 3 to infinity in that case. Well, the problem that we just asked for is this one, right? Which is not dissimilar. One way to attack this would be to begin with some algebra. I can flip the inside over, write it as n plus 1 over n, if I make the power negative. And now the inside, I could write as 1 plus 1 over n raised to the negative n squared. This would be one way to begin. And then hopefully comparing the series that we get here to the one that we did at the start of the review, you can kind of see how to go from one, you could solve this one by using the root test the same way we solved this one using the root test. But if you wanted to begin fresh, if you didn't see that those could be like related to each other, the root test always asks you to compute the limit as n goes to infinity of the nth root absolute value an. And in this case, that's going to look like the limit as n goes to infinity of the nth root absolute value of n over n plus 1 to the n squared, all in absolute values. And sort of just like that earlier example, I can argue that the inside here is definitely positive, right? N over n plus 1 as n goes from 1 to infinity is positive. So that all raised to the n squared will certainly be positive. So I can lose the absolute values. It's important that you begin with the absolute values, but then you can drop them in the next step. And I'll rewrite that power as, that root as a power. So I've got n over n plus 1 to the n squared, all raised to the 1 over nth power. And then simplifying algebraically, I get n over n plus 1 raised to the n squared times 1 over n, which is lim n to infinity, n over n plus 1 to the n. Now I'm inclined to say I'm going to leave it here, both because we're out of time, but also because I don't want to resolve every instance of a limit we bump into like this for you guys. I think this would be a good case where you should try to take it from here to the end. So if you're jumping in and you didn't see anything else to do, the most natural thing to do would be this, right? They told you use the root test. We don't do any funky algebra beforehand. You just dive in blindly with the root test, and within 1 or 2 steps, you will get here. The question is, how do you handle this limit? Now notice that the inside here is going to 1. All right, if you renormalize inside, you'd have 1 over 1 plus 1 over n. So the inside here is going to 1, but the power is going to infinity. So this is an indeterminate form of the type 1 to the infinity. And regardless of which section you're in, we got a little bit of a discussion on those on Friday. So I would try to see this as one of your e to the ab limits, just as is suggested by this and the similar problem from earlier. But that is it, all right? So I got to get running, guys. Unfortunately, I've got a handful of other important things I need to be doing tonight. But if you do get stuck on anything else, please send me a Canvas message. And if you want to submit your study guide, I will work on getting you some feedback on those as quickly as I can when they come in. All right, I will see you guys. Let's see, I guess either in office hours, Monday or Tuesday, or in class on Wednesday. Oh, let's see, we got a question here. +2. Oh, okay, yeah, okay, cool. All right, take care, guys.